Professor Ogi is a professor at Department of Precision Engineering, Graduate School of Engineering, Osaka University. Professor Ogi research area and expertise is about ultrasonics, nanomechanics, elasticity of solid materials, thermal mode spectroscopy, picosecond ultrasonic, resonant ultrasound spectroscopy, non-destructive evaluation with electromagnetic acoustic transducer, uh, bio and gas sensors, ultrasonic acceleration of protein fibrillation. Okay, uh, so that's a brief introduction of Professor Ogi. So without further ado, now I would like to invite Professor Hirotsugu Ogi to give his lecture for today. Professor Hirotsugu Ogi, the time is yours.
Okay, thank you for introduction. So I will share my slide. Okay, so can you see my slide, top page? Without
Yes.
problem? Okay.
Yes, we can see.
Okay, so hello everybody. My name is Hirotsugu Ogi. I am a professor at the Department of Precision Engineering at Osaka University. So today I would like to show the ultrasound techniques for evaluating the elastic constants of small materials. And I will show two techniques. One is resonant ultrasound spectroscopy. Here you can see with which we can determine all of the independent elastic constants of very small materials at high temperatures and even very, very low temperatures. The second method will be the picosecond ultrasound, in which we can generate very, very high frequency ultrasound, very high frequency, exceeding 100 gigahertz. And in such a high frequency ultrasound, it is possible to very accurately evaluate the elastic constant of a thin film. Okay. This moment. So, okay. So here are contents of this lecture. First, briefly, I would like to explain the Fouquet's law and the elastic constants. And next, I will show the resonant ultrasound spectroscopy. This method is called RUS method, or just Rdus method. And then I will show the picosecond ultrasound, and then I will show the first principle calculation method for theoretically calculating the elastic constants of solids. And I will go for summary. Okay, so I hope you know this word, stress. When we apply the external forces to a solid, the internal force appears on a cross-section of the material, inside the material. And the stress is denotes the internal force divided by the cross-section area when we take the limitation of the cross-section area to be 0. So the stress has the same dimension as the pressure. And but it can be defined at a point inside the material because we take the limitation to 0 cross-section area. And because we can use 3 kinds cross-sections along X, Y, and Z directions. And also the internal force, of course, has 3 components along X, Y, and Z directions. Therefore, stress has 9 components. For example, sigma xx denotes the internal force along x direction acting on the plane normal to the x direction. And for example, sigma yz indicates the internal force along the z direction acting on the y plane. That means a plane normal to the y-axis. Okay, and the stress has 9 components. And this is a strain tensor, which is given by the 3x3 matrix. However, we can easily prove that the strain tensor is a symmetric tensor, so that the sigma ij equals sigma ji. Therefore, there are only 6 independent stresses. 6 independent stresses. They are sigma xx, yy, zz, yz or zy, zx or xz, and xy or yx. And these 6 stress components are denoted by T1 to T6. Okay, so these are stresses. And when we cause a stress inside the material will deform. Okay, and the index of deformation is strain. This is a very good index of deformation of the material. This is a non-dimensional degree of the deformation of the material. And this has also 9 components, and each component can be expressed by the gradient of the deformation vector. Deformation vector U. U is a deformation vector, which expresses deformation from before to after. Okay, and clearly the strain component is shows the symmetry. That is epsilon ij equal. Oh no! Oh, this is miss. This epsilon ji. So that also 6 components can be considered. So that and then we take them. We show them from S1 to S6. However, we have to note that in case of the strain, so we need to factor 2 for the non-diagonal components. So that for the diagonal components, we can set S1 to equal epsilon xx, for example. But for example, in case of the S4, we need the factor 2. Okay, which must be multiplied to the non-diagonal component because of the. Okay, so I'll explain that. Okay, anyway, we apply the when we apply the external force to the material, and if the stress appears, then deformation occurs, and usually. The stress component can be expressed by the linear combination of the strain components, like this. In case of the tensor notation, like this equation, and in case of the matrix notation, we have this equation. Anyway, in any case, so stress and strain are related linearly with the material constants, that are elastic constants. So this is called Hooke's law. Hooke's law. And these components, elastic constants, dominate how the material deforms when they receive the external force. Okay. And also from the energy consideration, we can prove that the elastic constant matrix is also a symmetric matrix. And then in this case, okay, we have maximum 21 maximum number of the independent elastic constants. However, usually we don't need to take the 21 because of the symmetry of the material. Okay, for example, anyway, so this is elastic constants and very, very important parameters. And the elastic constants reflect the resistance to deformation. Therefore, they are needed in designing any structures, including very big materials, cars or biomaterials, or devices, very, very small materials, very, very small structures. In designing these structures, we must know the elastic constants because they determine the deformation behavior of the material. And also, scientifically, it is very important material, very important parameter because the elastic constant reflects the interatomic potential. Okay, because it is given by the second derivative of the internal energy U with respect with strain. So if we know the elastic constants accurately, so then they can be calculated theoretically using the theoretical model. But to evaluate the accuracy of the theory, we need to know the elastic constants. Okay, so we have to compare the elastic constant. Not only the lattice parameter, also the elastic constants are also very much important to evaluate the to validate the theoretical calculation. Okay, so elastic constants have many independent components, but because of the symmetry, the number of the independent elastic constants can be decreased. For example, in case of the cubic materials, so there are only 3 independent elastic constants. And in case of the hexagonal material, including gallium nitride, aluminum nitride, titanium, and so on, and in this case, we have to know 5 independent elastic constants. And in case of quartz, there are 6 independent elastic constants. And in case of the monoclinic materials, such as the beta gallium oxide, 13 elastic constants are needed. And to know, we have to know all of them. Otherwise, we cannot design the fine devices. Okay, so very difficult to determine them. And then how to measure the elastic constants? Okay, so from the definition, the elastic constant is given by the applied force or stress divided by strain. So then you measure the stress or force and the deformation. Then you can obtain the elastic constant. So classically, like this test, this is a tensile test. Okay, this is a material, rod-shaped material, and we apply the tensile force. Then we measure the deformation or strain. Then we can get one component of the elastic constant of this material. However, you can see that this method is not cannot be used to very small materials. Of course, for example, thin film, we cannot make the reliable tensile test for thin film, for example. Then the sound has been used for accurately measure the elastic constants. So typical way to measure the elastic constant without the sound is to use the Picosecond technique. Okay, so I will omit the explanation, but the sound velocity is dependent on the elastic constant and the mass density. So mass density can be obtained from the interatomic distance or the lattice constant. So that can be measured by X-ray, for example. So mass density can be measured, but elastic constant cannot be measured easily. So that, but by measuring the sound velocity accurately, so it is possible to determine the elastic constant from the sound velocity. And the typical method is the pulse echo method. So here is the material, examine the material, and we put the ultrasound transducer, and we send the short sound pulse to the thickness direction of the material. The ultrasound wave propagates along the thickness direction, then it repeats reflection between two surfaces. Then we will see a train of pulse echoes like this. This is the first echo, second echo, third echo, fourth echo, and so on. And from the round trip time, delta t, it is possible to determine the sound velocity. And because we know the thickness of the material, so that we can calculate the sound velocity and then the elastic constant. So this is a pulse echo method. However, this is also not so very good method for very small materials and low symmetry materials. And as I showed, so for example, in case of the cubic material like silicon, there are 3 independent elastic constants. And to determine all of them, we have to measure the sound velocity propagating along the different directions. For example, this direction, this direction, this direction. And then we have to prepare the plate-shaped specimen with different crystallographic orientation, so that meaning that the material must be very large, so that then we can cut from the different orientations. However, if the material has 1 millimeter by 1 millimeter by 1 millimeter cube, for example, so we cannot cut different materials with different orientations, so that this can pulse echo method cannot be used in such a case. Okay. Then we use a resonance method. Okay, so the resonant frequency of solid also depend on the elastic constants as the sound velocity. For example, you know this system consisting of the point mass and the spring, and in this case, the resonant frequency is given by square root of k. K is a spring constant divided by m. So the elastic constant is like the spring constant between atoms, so that by measuring the resonant frequency of this system, we can determine the spring constant if we know the mass. The same thing occurs for the continuous solid. Okay, so in this this method is very much useful because by measuring many resonant frequencies, then we can determine all of the independent elastic constants from a single material, single small material. Okay, so this method is the resonant ultrasound spectroscopy, or RUS method. So because the free vibration resonant frequencies of a solid, there are many free vibration resonant frequencies of a solid, depend on the mass density, dimensions, and all of the elastic constants. So then by measuring the density, dimensions, and many resonant frequencies, so we can determine all of the independent elastic constants inversely. Okay. So for example, using this device, we can measure many resonant frequencies of more than 100. So in this case, we used 2 ultrasonic needle transducers. So this is a one transducer, and we cause the sinusoidal voltage to apply to this transducer, which causes a vibration to the material. This is a specimen. In this case, the specimen dimension is about 5 millimeter in cube. And then the vibration of the specimen is measured by the other ultrasonic transducer, piezoelectric transducer. Okay, and by sweeping the frequency of the driving sweeping frequency, this is a frequency of the input frequency, and then measuring the amplitude of the detected signal. So we can detect many resonant frequencies like this. And each resonant frequency, all resonant frequencies are affected by the independent elastic constant, but the contributions of each elastic constant is different for each mode. So by measuring many resonant frequencies, it is possible to obtain independent elastic constants simultaneously through the inverse calculation. And this is a very simple method. Just we put the specimen on the tripod, and then we make the one single frequency scan to obtain 100 resonant frequencies. Okay, so very useful for very small materials. And also, it is useful to measure the vibrational pattern using the laser Doppler interferometry by scanning the specimen surface with a laser beam. So, for example, for this vibrational mode, we obtain this vibrational pattern on the top surface. So darkened region indicate the nodal point, and brightened region indicates antinodal points, and like this. So that these are mode figures can be obtained by measuring the surface deformation distributions, and it is possible to compare them with calculations to identify accurately the observed mode. This is very important in the inverse calculation, because we must compare the same mode in the calculation and the measurement. Okay. Otherwise, obtained elastic constants are physically meaningless. Okay, the calculation of the elastic constant and the mode figures can be made possible very accurately using the Rdus method. So Lagrangian of the solid in case of the free vibration is given by this equation. This is a strain energy, and here is the kinetic energy. And using the Hamiltonian principle, we obtain the eigen value problem, and from the eigenvalue we can get resonant frequencies, and from the eigenfunctions or eigenvectors we can obtain the vibrational pattern. So then to make the we can make the inverse calculation. Okay, and for example, this method was applied to the beta gallium oxide, which shows 13 independent elastic constants. 13. So this material was, the structure was identified in early 19th century, and still, and already many applications have been this material was applied to many applications, especially for power device. But there was no report on elastic constant, despite nearly 100 years ago this material was discovered. But recently we determined we have succeeded all of the independent elastic constants of this material. Okay, with this method, okay, I will make details. This is a Rdus method. Okay, so the next topic is the picosecond ultrasonics. This is a kind of the laser ultrasound technique. For example, this diagram, this figure shows the cross-section view of thin film deposited on a substrate. And when we irradiate the specimen with femtosecond laser pulse, very, very short pulse, then very high frequency acoustic wave is generated. And it propagates along the thickness direction and reflects at the substrate surface and repeat reflections inside the material, thin film materials. And normally, the time to travel inside the thin film is too short to be detected using a digitizer. However, using a pump probe technique, it is possible to measure the waveform with the time resolution as short as 50 femtosecond. So it's possible to detect ultra-fast propagation of the sound wave like this. This is the actual measurement result. So this shows the pulse echo signal for platinum thin film deposited on silicon substrate. And the thickness of the platinum is only 70 nanometer. It's very thin. But you see clearly the pulse echoes. Okay, the horizontal axis is time, and can you see this is the unit is the picosecond, so that very, very short time. And even such an ultra-fast phenomenon, it is possible to detect the pulse echoes clearly, so that we can measure the round trip time and then the sound velocity propagating inside the thin film. Then we can determine the elastic constant of this material. So this is a picosecond ultrasound technique. And this is a pulse echo method. And in our feeling, the 70 nanometer is still too thick. Okay. And if the material is thinner, then the resonance occurs inside the sound thin film or nanostructures. For example, in case of the thin film of cobalt platinum alloy with the thickness of about 30 nanometer, in this case, you can see the resonance occurs by applying the pump-right pulse with femtosecond time duration. Okay, so and the resonant frequency is about 100 gigahertz or something. So, and from the resonant frequency, we can determine the sound velocity and then the elastic constant. Okay. So, in this case, nearly 100 gigahertz ultrasound measurement is made possible. And we can further increase the frequency of the sound wave with this technique. So next, okay, next is that next shows the Brilliant oscillation method. This is also the picosecond ultrasonics. Okay, in this case, we add very thin film. For example, 10 nanometer or 5 nanometer aluminum film on, for example, glass specimen. And we again apply the pump-right pulse. Okay. And because of the transient thermal expansion, the very high frequency acoustic pulse, acoustic wave propagates along the thickness direction. Then we cause the probe-right probe-right pulse, okay? And the probe-right pulse to detect the sound wave. So it will reflect at the surface, but it can penetrate into the specimen because the aluminum film is very thin. And in case of very high frequency elastic wave, ultrasound wave, so the wavelength is close or shorter than that of the probe light pulse, probe light. Then, because of the black diffraction, so backward diffraction occurs from the of the light from the acoustic pulse. So the ultrasound wave can reflect the light when its wavelength is very, very short. Okay, and then the interference occurs between the probe light pulse reflected at the surface and the diffracted light. And because ultrasound wave propagates along the thickness direction, so the phase of the diffracted light changes. And then, okay, so oscillation is observed in the total reflectivity of the probe light pulse. And this oscillation frequency is equal to the frequency of the sound wave. For example, in case of the glass thin film, 45 gigahertz frequency is obtained. And then when the sound pulse reaches at the substrate, silicon substrate, the frequency of the detectable sound pulse increases significantly. In this case, a 235 gigahertz frequency, meaning that we can measure the sound wave velocity at exceeding 200 gigahertz frequency with this technique. So very, very, very high frequency measurement is made possible. And note that in this case, the wavelength of the sound is about 10 nanometer or 20 nanometer, which is significantly shorter than that of the light pulse. So, okay, usually the wavelength of sound is recognized as very, very long compared with that of light. But in our measurement, the wavelength of sound is shorter than that of light. Okay. So this is one example of optics we developed to achieve such a measurement. And I omit the detailed explanation, but in this case, we used 2 pulse lasers. And one pulse laser caused the vibration inside the material, and then the other pulse laser detected the vibration to see a piezo optic effect. Okay. And this measurement is made possible at low temperatures and high temperatures as well. And using this method, we have succeeded in synthesizing the ultra stiff diamond. You know, a diamond shows the maximum elastic constant. Okay, and many people searched a material exceeding the showing the stiffness exceeding the diamond, but they failed. But we succeeded. And using the special synthetic technique, and we have succeeded in making a very nanopolycrystalline diamond, and which shows many twinning structures. And okay, so time is not okay. Anyway, so twinning structure can cause the increase in the stiffness very much, so that this was the first discovery of a material whose stiffness exceeds the diamond. Okay, finally, briefly, I will explain the calculation method of the elastic constant using the ab initio calculation. And because the internal energy is expressed by this equation, so strains and the elastic constant, so by calculating the energy by changing the strain, it is possible to determine the elastic constant theoretically. Okay, So first we determine the relaxed structure, and we apply strain and relax ions, and then we can calculate the total energy. Then we fit the harmonic functions, then we extract the coefficients, that is the elastic constant. And to perform such a calculation, we need to form the deformation matrix D, which is dependent on the strain tensor. And then from matrix D, we can calculate the basis vectors after the deformation with this equation. And for example, in case of if we like to determine C11, this component, then deformation vector takes this form, then the strain energy is given by this equation. So that by changing the strain from, in this case, -1% to +1%, and measuring the energy, total energy, so then by fitting this function to this result, we obtain the C11, okay, from the coefficient of the fitted function. And in case of C12, so the deformation matrix takes this like this, and then in this case, the strain energy is given by this equation. And because we know C11 and C22 previously, so that C12 can be obtained by changing the strain value and by measuring the total energy and by fitting this function to the measurement. Okay, so using such a calculation, so we can determine all of the independent elastic constants theoretically. However, this is very important. However, the calculation result is very much dependent on the potential you use. The typical potential, LDA and GGA. For example, in case of the ultralight boron nitride, in this case, the lattice parameters are very much evaluated with GGA, but the elastic constants are much better by using LDA. So then, in this case, we need to use a hybrid GGA method and so on. So anyways, it's very important. And that's why the elastic constants are very much important. If you compare your result with only with the lattice parameters, so that not perfect result will be obtained. So I recommend you to always use the elastic constant by checking your calculation. Okay, so here's the summary. The elastic constants are very important, both practically and theoretically, scientifically. And the measurement of the elastic constant is usually very much difficult, but okay, so this is important. So this is a very, very important message from. So please do not believe easily the reported values in literature and handbooks, especially for small materials, including nanowires or thin film and so on. Maybe they are incorrect. And the DFT calculation result is significantly dependent on the calculation condition. So measurement of the elastic constant is then very much important for evaluating the validity of your calculation. Okay, that's all from my presentation. Thank you.
Okay, thank you very much, Professor Ogi, for very nice and interesting lecture. So now we will go to the question and answer session. We have 3 questions in the chat box. So I will read the first question. First question is, what are limitations between 3 methods, pulse, echo versus resonance versus RUS?
Okay, so just a moment. Okay, in case of the RUS method, so we cannot use the very large specimen. Okay, very large specimen. Also, maybe a too small specimen cannot be used. I would say 0.5 by 0.5 by 0.5. 0.5 is the minimum with this method. And in case of the picosecond ultrasound, just a moment. So, okay, so this is actually a very powerful method for thin films and nanostructures, but the important thing is that only longitudinal wave can be measured because we excite the ultrasound wave with the thermal expansion. So we cannot cause the shear wave usually. So for example, we cannot evaluate the shear modulus of the thin film with this method. Okay. Is that okay?
Yes. Maybe we move to the next question. If I want to compare stress versus strain the material of cellulose, which contains silica, how could possibly be measured?
Okay. So if that material is large enough, okay, large enough, so you can use the conventional pulse echo method. Okay, then the silica, I don't know the diameter of the silica, but with the ultrasound technique, you can obtain the macroscopic elastic constant. And the elastic constant of silica is reported. And you have, if you know the volume fraction of silica, then it is possible to evaluate. So your question is the how could possibly measure? So what do you like to measure? Okay, so if you like to know the macroscopic elastic constant, so maybe you can use a conventional pulse echo method. Can you see this figure now? Or maybe yes. Okay, so I think that your specimen is not so small. So for example, 5 millimeter in thickness you have, then in this case, you can use the pulse echo method, typical pulse echo method. So you don't need to use RUS method, or you cannot use a picosecond ultrasound because your material will be too large. Okay.
Professor Ogi, can I explain my question? Actually, I'd like to make a flexible anodes or cathodes in a flexible battery, which thickness around maybe in millimeters, yeah? quite thin. So, with your method, is it possible to measure the stress and strain combination?
So, what do you like to measure is the elastic constant. Is that okay? Or do you like measure stress? What do you like to measure? The elastic
actually,
constant?
in detail, yeah, there are two different type of cellulose which combine each other.
Okay.
If one cellulose typically easily to break, and another is too flexible, and which is I don't like. I'd like to combine these two different material. So we have a very good texture, very good flexibility, which is not easily to break, but also quite strong.
Okay.
Do you understand what I mean, Professor Ogi?
So so your voice is sometimes broken. So please say again. Your mic is not so good.
Okay. Okay. Actually, I want to
measure. Do you like to measure the elastic stiffness of cellulose? What do you like to measure?
Yes.
Okay, stiffness of cellulose.
Because.
Okay.
Yeah.
And how much is the thickness, for example, of that material?
Roughly. I think below 1 millimeter.
Below 1 millimeter. Okay.
Below 1 millimeter.
Okay. In that case, how much is the dimension in plane dimension? For example, 5 millimeter by 5 millimeter, for example, or more?
I think 1 centimeter times 1 centimeter.
So in that case, I think you can use a typical ultrasound technique, pulse echo measurement. with high frequency ultrasound transducer inside water, for example. So with frequency exceeding 100 megahertz, in that case, I think you can measure the sound wave or cellulose using the pulse echo method. So 100 micrometer thick is not so difficult using the high frequency ultrasound. I mean, you don't need to use RUS nor picosecond ultrasonics. I would say that you can use a conventional ultrasound method in water. Okay. But you need to use very high frequency transducers as high as 100 megahertz, for example. If the material is thin, as thin as 0.1 millimeter or something. Is that okay?
Yes, thank you very much.
Yeah, okay. Thank you, Professor Ogi, for the answer. So we move to the next question. Can ultrasonic techniques be used to measure elasticity in elevated temperature?
Yes.
Example, 500 Celsius, and can it measure elasticity in polycrystal material?
Yeah. Using for example, using the RUS method, so we can put the silica rod between the specimen and the piezoelectric transducers. Then we can increase the temperature more than 1,000 degrees Celsius. So it is possible. So there are many measurements at high frequency, at high elevated temperatures.
Oh, okay. Yes. Okay. Yes. Okay. To all participants, do you have any other question? Maybe you can type in the chat box or you ask directly. Okay. I think there is no other question, Professor. Because of that, maybe we conclude our second session for today. I would like to thank you very much for your lecture. We really appreciate it. And yes, thank you.
Okay, thank you.